We have our first day of exponential growth and decay functions. I'm going to have you guys start by uh, putting in some values for, actually, I'll give you the values for x that I'd like you to put in, but you're going to be putting them into these two functions right here. So I'm going to have you put these values in here. How about we go negative 1, 0, 1, 2, and 3. Let's start with those. And you're going to be putting them into the y sub 1 function, which is right here. And those y values you're going to be putting in that first column. You're going to be putting them in the y sub 2 function right here. We'll put those values here. All right, so that's the first function. What do you notice is happening between each of those y values? Like, what's happening? They're doubling, right? Why? What number is making it do that? The 2. The base of this function is 2, so it doubles it. Now, we said, when you put that negative 1 in, it flips it, makes it 1/2. If you put a negative 2 in, what would it make it? 1/4, right? Positive 1/4. And in fact, I might add that one down here. If we were to put negative 2, so this is kind of bad, I have these not in order now, but if I put negative 2 in, it would be 1/4. If I put negative 3 in, it would be 1/8. I'm just going to put the negative 2 there, just put one more value in there. I probably should have put that at the top, but that's good. All right, so now that we have those values, when you start doing that blue function, look at the order of operations. You're going to be doing the exact same thing we just did in the red function, except you're going to be multiplying it by what? So in other words, you can take all those values that we had in that first function and just multiply them by 3. In other words, the y sub 2 function is really just the y sub 1 function times 3. So I'm going to multiply all those values that I already have there by 3 and get 3/2, 3, 6, 12, 24, and then 3/4. That's really why I added that bottom one, that negative 2, because I knew for this function we would get 3/4, and that's graphable. It's about 1. But some of these aren't. Like that 24 we probably won't fit. It's close, but we won't. So let's graph each one of those. Any questions so far? These are powers of 2 in that red column, that y sub 1. The second column are the powers of 2 multiplied by 3, which is exactly what those functions say. All right, so let's graph that first one. We got 0, 0, 1. We got the negative 1, 1/2. We got 2, 4, 8, 16. Do we even have that? No. I could go 16 on my next one here. Where is it? There it is. I wanted to get one more on there. So there's that first function. Now, that is not what we want to do, what I just did right there. That's not good. We don't want to just like have the function start there. Just because the first value I put in was negative 1. Actually, we did put a negative 2, didn't we? We got that negative 1/4, okay? This thing goes on forever to the left, right? Forever and ever and ever. It just keeps getting smaller and smaller and smaller. Will it ever actually equal 0? No, so, that's not really, I'm going to do that one again, actually. I'm not very happy with that. If you make it touch this axis, I'm okay at that. Just try not to go below it. Definitely, we know that if we zoomed in as tight as we possibly could, if we could zoom into this thing as tight as we possibly could, it would never, ever, ever, ever touch that axis. Because you couldn't take 2 to a power and ever get 0. Even if you took 2 to the negative whatever, negative 1,000th, it'd be a really small number. It would be almost 0, right? To us, it's pretty much 0, but we know that it really is a number that's just a little bit bigger than 0. So it gets really close to that axis. It never crosses it, okay? If you end up like touching it in your graph, that's fine. Just don't go below it. Don't go below it like that. That's not good. And don't bounce off of it either, okay? That's not what this does. Just get really close to it. So let's talk about domain then. This thing goes forever to the left, right? So we know that the domain starts at negative infinity. And then going to the right, even though it looks like it goes up, are the x values still growing? Yeah, you can put anything in for x. This goes all the way up to positive infinity. What about the range of that guy? Are there any negative numbers? No, so the smallest number is 0, but does it actually equal 0? No, we just said that. Could never, ever actually equal 0. So make sure you use a parenthesis there with 0. It gets really, really close to 0, but it never actually equals it. Okay? All right. That means that there's an asymptote right there, a horizontal asymptote that tells us about the left end behavior of this function. That asymptote is the x-axis, or y equals 0. And it's a horizontal asymptote. Exponential functions have horizontal asymptotes. All right, if you haven't yet, go ahead and graph that blue function. All right, so I have the 4 values. I have -2, comma 3/4. I have -1, comma 3/2. I have 0, 3, and I have 1, 6. Those are those. And to get those, you guys, I didn't even look at my table. I just looked at the y values that my red graph had, and I multiplied them by 3. So for example, at this one here, I was like, okay, I'm going to multiply that by 3. It's a 1 right now. 1 times 3 is 3, and that's why I put the 3 there. Same thing with all the rest of them. Then as soon as I got to the 2, comma 4, oops, I don't know if I didn't do that one. If I multiply that by 3, I get 12. There's that one. But as soon as I get to the 3, comma 8, when I multiply that by 3, I know that the 8 becomes a 24. I can't even fit that. So this is pretty much all we're going to have here. Notice that this thing, it's not that it got shifted at all. It just got stretched. In other words, that 3, that's an a value. Remember how we've always talked about a as a vertical stretch or shrink, right? With every function that we've ever done, a is a vertical stretch or shrink. This thing stretched it vertically by 3. All right, so that's why we multiplied all the y values of that first function by 3. All right. Any questions on that at all? All right. I'm really glad that I'm recording this because this is the first day after spring break, and some of you are really struggling to find excitement in this, which is weird because this is fun stuff. Schaefer, if you don't calm down back there, I might have to remove you from the room. All right? That's on video. It'll be here for years to come. I hope I have your brother in class one day. All right. So let's look at this next one here. This is a base now of 1/2. So what I'd like us to do with this one is let's just do with the y sub 1. Let's just ignore that. Let's ignore that 3 and just do 1/2 to the x. And then in this one, let's treat that a value like we have in the past. Say a equals 3, we'll multiply all those y values by 3. So it's like taking it a step at a time. Now here's the deal with this one. Think about what the values that you want to put in. If you put a bunch of like values like 1, 2, 3 in there for x, these numbers are going to get really small, right? So let's put some negative values into this one. Like, I don't know, -4. I have no idea why I went with purple. -4, -3, -2, -1, 0, 1, 2. I don't know if that's going to be, I'm going to go with a 3 down here too. We'll see what that gives us. Actually, no, we don't need that. We're good. So if you put the -4 in, okay, now remember, when I'm doing this, I'm ignoring that 3 out in front. I'm just looking at this right there. I know that when I put these negatives in, it's just going to flip it and basically turn that base into a what? 2. So when I have a -4, I'm really just thinking about what is 2 to the 4th. So 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. 2 to the 1st is 2. Anything to 0 is 1. Okay, now I'm gonna like backtrack just to make sure we know that I really do have a 1/2 as my base. So 1/2 to the 1st is 1/2. 1/2 squared is 1/4. Notice that those are all going down by a multiple of 1/2, right? That is not a coincidence. That's because that's our base. Now let's go ahead and take care of the fact that that's a 3. And you could do this all in one column if you wanted to, if you were making a table. And you probably wouldn't need this many values either. The 16, that's going to become a 48. Don't think we're going to fit that. 8, we have 24, 12. We're just multiplying all those y values by 3. Now this is the only thing we're graphing here. This is the only one we're going to graph. So I'm going to graph pretty much just these values right there. So take a second, go ahead and graph those. All right, so that's the graph that I have there. I just plotted those values. What do you notice about things like the asymptote here? Has it changed from the last one? No, still horizontal asymptote at y equals 0, the x-axis. I didn't put that stuff again. That stays the same. How about the domain and range? Have they changed at all? No, the domain is still all real numbers, and the range is from 0 to positive infinity. Nothing has changed. This stuff is all the same down here. Okay, I don't know if you need to write something like that or just remember that stuff is all the same down there. Okay, now here's the big thing though. That first set of graphs, there's two of them. That is an example of exponential growth. What is this example C? Exponential what? Decay. All right. So when you have an exponential model, y equals a times b to the x. I'm just going to put a couple of definitions here. This is our base, our exponent, obviously. That's our exponent. You know that stuff. But the exponent is the independent variable here. Okay. What makes an exponential function is that your variable, your independent variable, that's what the I and D there is, independent. Your independent variable is in the exponent. It's the only type of function that we deal with that's like that has a variable in the exponent. That's what makes it an exponential function. Okay, it's not like our polynomials that have the variable taken to an exponent. Now the variable is the exponent. So A represents an initial value in these. Okay, if you look back at every graph that we did up above, the y-intercept was the A value. Okay, so A is an initial value. We especially use that idea when we're doing our application problems, or y-intercept. And it's a vertical stretch or shrink. Vertical stretch or shrink. Okay. With the application problems, it's good to think of A as an initial value in the problem. In these generic just graphs, it's good to think of A as a stretch or shrink. We know that it'll be exponential growth if that base is greater than 1, but it will be exponential decay if the base is between 0 and 1. You can't have a negative base. That would not be considered exponential growth or decay. That'd be a whole different thing. So in order to be an exponential function, the b value has to be positive. It's got to be positive. If it's between 0 and 1, then it is growth. Greater than 1, or excuse me, if it's between 0 and 1, it's decay. If it's greater than 1, it is growth. All right, any questions at all? Okay, one last time I'm going to have you right here. Just going to have you throw these things down here. Just some examples. Right here, right, y equals 3 times 1.4 to the x. Is that growth or decay? So let's write is growth. That represents growth. The growth rate is, I haven't even thrown this definition out there yet. What's the rate that's growing? How much bigger is that value than 1? The base. 0.4. That means that it's growing at a rate of 40%. Or you could just say 0.4. Y equals 3 times 0.4 to the x. This time that's decay, right? The decay rate is, well, how does that differ from 1? 60% or 0.6. That would be the decay rate. Every value is 60% less than the one before, because the decay factor is 0.4. Okay, B, that is known as the decay factor or the growth factor. So for this one, we could say the growth factor is the decay factor. But the difference between that B value and 1 is your rate, that you're either growing or decreasing. So in this case, I'm just going to put underneath here, the growth rate would be found by taking B minus 1. In our little example that we wrote down there, we had 1.4. Take 1.4 minus 1, you get 0.4. That's your growth rate. To find the decay factor, since it's it's less than 1, we want to actually flip that. The decay rate is found by taking 1 minus b. That would give you the decay rate. Questions on those at all? All right, moving on. So the other thing that could happen at the A values, it could become negative. All right, now, first let's start with this. Is this growth or decay? And never mind this thing right here. Is this growth or decay? It's growth because B is 2, right? It's definitely growth. Now, when we get done graphing this thing, because of that negative, what do you think that negative is going to do to the graph? It's going to flip it. So instead of it looking like this, it's going to flip it. It's going to look like this. So that's what our graph is going to look like in the end. Let me just draw that up here so we can see a little bit better. That's what our graph is going to look like at the end. It's going to have a horizontal asymptote right there. That's still called growth. It's weird. But in an application sense, we probably wouldn't use this and call it growth. But it's still considered growth. It's just growth that's been reflected because of a negative A value. All right, so let's see what happens here. Let's take this in the same steps that we did before. Let's I got the 2 columns here. I'm going to just put in some of these values, -2, -1. They're the same ones from the front side of this thing because we're dealing with that same base of 2. I just use the same base route so that we could compare all these graphs. So for y sub 1, I'm just going to be looking at y equals 2 to the x, which is the same function that we've been dealing with. So we've got 1/4, 1/2, just doubling these each time, 1, 2, 4, 8, and 16, just taking powers of 2. But now here's the actual graph that we're going to graph, and that is when we have an A value that is equal to -2. We're going to multiply those all by -2. It's going to give me a -1/2, -1, and so forth. And then we'll plot those. Notice as you plot those that even though this thing is going down, your y values are doubling, still because of that 2. Doesn't matter that it's got the 1/2. That 1/2 affects the initial value, that where it crosses the y-axis. Okay, that it did shrink it. I'm sorry, not 1/2, the -2. Okay, I should say it did stretch it and reflect it. Okay, so this is a vertical reflection. And then here we have the fact that its growth is because of that 2. Questions as to where any of those values come from at all? Are we okay at that? Okay, because now what we're going to do is we're going to shift these things. It's a very generic start to these sections. Okay, we have no application problems yet. It's just how do you deal with these functions? And really, this is a lot of review for us about how these things, H, K, A, how they all reflect it. All right, so just like we've done in the past, A is a vertical stretch or shrink. If A is negative, we reflect it over the x-axis. Okay, that's really what happens, even though sometimes we kind of move stuff first and make it look like it is reflected later. H shifts it horizontally, K shifts it vertically, just like always. H is the opposite of what you see, and K is the same. And then it says, this is very similar to other functions we have graphed. So to graph more efficiently, we kind of create a temporary origin at HK so that y equals K is actually a horizontal asymptote. And we kind of treat that HK value as the origin and we graph from there. From there, we would graph y equals A times B to the x without the H and K. It's everything that we've done in the past, just with a new function. Okay, so write that stuff down there first, and then we'll start doing this example. And if you're kind of confused by that, hopefully it'll make sense as we go through this. So here's what I mean. I need you to understand that there's a parent graph hidden in all of this stuff right there. Okay, that parent graph is y equals 2 to the x. The A value is -3, right? The A value is -3. I'm just going to write that right there. A equals -3. What's our HK values? Or what if I had to write what HK, what is that? Like a point. -5, +4, right? It's opposite H, same K, okay? So here's what all this means. We're going to stretch this vertically by a factor of 3. Because it's -3, we're going to then reflect it over the x-axis. And we're going to shift it left 5 and up 4. That's what all this means. But we're not actually going to do that. This is that thing where we kind of cheat a little bit. And we find that HK point. Go ahead and find that HK point down here, that negative 5, 4. And you can put a little dot there if you want to. Negative 5, positive 4 is right there. Okay, I'm going to treat that like my origin. And I'm definitely going to put a dashed line right there. There's my horizontal asymptote. Okay, if you want to put a dashed line at negative 5, 2, you can. But really, that is just, I'm just using that as a, I'm going to put a little bit bigger point there so I can see it. I'm just using that as my origin right there. There is no asymptote right here. Okay, so be careful of that. There's only a horizontal asymptote. And I'm going to treat this like the origin. I am going to actually draw a light line in here so I can easily see that. I don't know if you guys can see that. So I'm treating this like the origin. All right, and now from there I want to graph y equals, again, I think we have 2 to the x for like the 7th time today. So if you want to do this all in one column, you can, but I'm going to start from scratch and do the whole. I'm going to put a couple values and just randomly picking some negative 0. Randomly picking some values here to put in. So I like doing this because these are so fast to come up with. Powers of 2. Well, this would just be 1/4, 1/2, 1, 2, 4, 8, and 16. So fast to come up with those. And now here's where I take that a equals negative 3. Since a equals negative 3, I want to multiply all those y values by negative 3. So we got these as our new values. And I don't think I'm going to fit in those last couple. But these are the points, this whole thing now, actually it's those 2 columns together represent y equals negative 3 times 2 to the x. And where do we want to graph that from? Yeah, from that HK point. Graph from negative 5, 4. Those points we want to graph from negative 5, 4. So from negative 5, 4, I want to go left 2, down 3/4. I'm going to go left 1, down 1.5. I have 0, negative 3, 1, negative 6 from that HK point. So I'm just doubling my y values now. And then I have negative 12. And that's all I'm going to be able to fit. Left that in here. Now, what I need you to understand is what really happens to this function is what we wrote right there, and it happens in that order. Okay, so picture this function, y equals 2 to the x. Picture that function in your head. We have it on the front page. Now picture stretching it by 3 vertically, and then flipping it, and then shifting it left 5, up 4, and you would have that graph right there. Okay, we just graph it more efficiently by going right to the HK point and going from there. Gloss, you good at that? Attaboy. All right, so, domain and range. What's the domain of this thing? Yeah, all real numbers, negative infinity to positive infinity. Range, got to be careful here. Go from bottom up. Yep. Negative infinity to what? To 4, inclusive or not? Not inclusive, so use that parenthesis right there. There's your domain and range. How about, what if I asked you for the horizontal asymptote? What would that be? Good. Good things to have on here as well. And that, my friends, there's your generic exponential functions.